For the last hands-on session, we will look into deploying models. So for that, first you need to again shut down the notebook that was previously running, the question answering notebook. You can go here to the running tab and shut it down. So when you open that notebook, you can just click the Restart and Run All button to let the training start already when we go through the notebook. Okay, so for this session, we will again look at the BERT model and we will fine-tune it, and then we will see how we can export that model so that it can be like run in kind of a standalone manner. So you won't need to like, for example, have Python around, or you won't need to have any of these data preprocessing or Glue NLP libraries around. So it will be exported in a standalone manner, and it can then be deployed to a cloud service. So in this case, we will use the AWS SageMaker service. But in principle, you could also, write your own deployment logic and run it on some private server or wherever you would like. So let's just do the obligatory imports in the beginning. Okay, and then let's get the BERT model again. So we use here the nlp.model.getModel API. We specify again the same data set. And we would like to have the pre-trained model on our GPU. So in this case, we will just download it. The model will be downloaded in the background, and we will now define a BERT classifier model. So that is to some degree similar to the BERT for QA model that we had before, but we will not classify each token individually, but rather we will classify the whole sentence as an input. So now we will initialize the weights of that classifier only and leave the other pre-trained weights alone. And then we do this hybridize call here, which is telling the model that we want to enable the just-in-time compilation. And now when we will do the first forward, when we will first do any computation with this model, so we input some data during fine-tuning, then just-in-time compilation will happen, and later we can use some export functionality which will export the compiled model so that it can be run outside of Python in a standalone fashion. So for the purpose of this session, we will look at the sentiment analysis example. So we will use again the IMDb dataset. We just get the train and test part. We have the BERT tokenizer again, and we have a transformation which preprocesses our dataset. So if we get the raw IMDb dataset that is provided by the Glue NLP API, then we will apply this transformation function that was just defined. So for that function, what we will do in this case is we will just take the text and the label, and we will map the labels, which I think range from 0 to 9 to range to be just binary, so 0 or 1. And then we will pass it through the BERT sentence transform function, which will compute the length of that sentence and will also give us a segment type. So in this case, we actually only have one segment. So we only input one sentence. We want to have the label of that sentence, whereas in the previous task we were always inputting two segments, so we were inputting the question and the answer, so there would be two different segment types, but here for this classification task we only have one segment type. So actually the segment type here returned by the transform function will be 0 for all the tokens in that sentence. So we can have a short look at how that looks now. So if we apply this transformation function to our dataset, we get our preprocessed dataset. And we can look at a sample. So, for example, the original sentence here would be something about this Bromville High cartoon comedy, and we will also, now get the tokenized BERT indices. So it will just look like this. But we can also look at the label. Well, it will take some time because the training of the model is running and this cell will now only be executed afterwards. So we will have to get back to it after the training has finished. So let's look at the training setup maybe first. So we will again use a BERTify function here. So the BERTify function, it will pad our input sentences to be the same length in the batch. We will stack the lengths of each sentences to one vector, and we will again pad the segment types here to be of the same length, even though all of them would be 0, and we will also stack the label, which would be 0 or 1 depending on the sentiment class. Then we can define our data loader. So our data loader will help us to create batches given the dataset and the BERTify function. And now for training the model, we will use the estimator API. So previously in the last tutorial, we used this myLearningRate handler. And I promised you that I will tell you how that actually works. So the myLearningRate handler here would be a handler that is passed to the estimator class and which will adapt the learning rate based on a policy that it implements. So in this case, we do a warm-up learning rate handling. So we will pass the trainer the number of warm-up steps, the number of train steps, and the learning rate that we target into the constructor. We will just save them. And we will also introduce an extra variable here, which is the step number. You set that to 0, and whenever the training begins, you will reset that to 0. And then whenever one batch is forwarded, so whenever we go to the next batch, the estimator will invoke this batch begin function here, during which we will just increase our count. And if we are still below our number of warm-up steps, then we will be warming up our learning rate all the way to the self.lr linearly. And once we have reached the number of warm-up steps, we will be decaying our learning rate from there on. And just at every batch, we will now here set a new learning rate to our trainer object, which is the one that will afterwards do the apply the gradient to the parameters of the network. So once we have defined this learning rate handler, we can also define our estimator now. So for the sentiment classification task here, with BERT, we will have to overwrite, or we have to inherit from the normal estimator and implement the fit batch function, because again we have a train batch which not only consists of the data and label, but rather in this case we have the inputs, the token types, and the sequence length. So now in this session also we show you how we can do that for multi-GPU training. So even though we have a single GPU available only, we can write this function in a multi-GPU compatible manner. So later when you instantiate that estimator, you pass it to contexts. So for all previous sessions, you were just passing the mx.gpu0 as a context, but you could also pass a list of multiple GPUs there. And now in the fit batch function, what we need to do is we need to look at each element x of our batch, which would be either the input, the token type, or the length. And for that input, we will split and load it to that GPU. So meaning, consider we have 4 GPUs. We would divide that input equally, if possible, in 4 same length subsets. And each of them we would load to one specific GPU. So that is done by this split and load function from the MXNet Gluon utilities. So then we have the train batch now split up into on each GPU. And we can compute the prediction output of the network. So in this case, we would execute a network on the input, token type, and sequence length for every input, sequence length, token type in our train batch. So essentially here, this list comprehension in Python, it will just, if we have 4 GPUs, it will execute the forward function 4 times, each time passing through the respective inputs on the correct GPU, given that we have executed a split and load function before. Then that gives us the prediction outputs. So we get a list here of 4 elements, which are the prediction outputs on each of these 4 different GPUs. And we can compute now the loss. So again, we make list comprehension where we input our output and the label for each part of the data on its specific GPU. And finally, we compute the backward function. So here we use this mx.autograd backward, and we give it a list of losses, and it will do the backward computation on each GPU independently and compute a gradient there. And then finally, if we now just call trainer.step, the trainer.step would aggregate the gradients from the different GPUs. So it would copy them over and then apply them. But here, for the purpose of this session, we will also use a gradient clipping trick. So actually, we want to first aggregate the gradients. We can use the all-reduced grads API to do that. So now the gradients on all GPUs will be the same. We have shared the information. And then we just use this utility function here, clip grad global norm, which will clip all gradients that have a norm like larger than 1 to be of norm 1. So it will look at what is the norm of the gradient of that parameter. If that norm is greater than 1, it will renormalize it. Otherwise, it will leave it alone. And then finally, we perform the update step, which is we actually apply the gradient to our parameters, and we get our updated parameters. So that is the fit batch implementation here. And if we instantiate that estimator now, we need to also pass it the trainer, the loss function, and the metrics. And importantly, we pass it our my learning rate handler here as event handler. So then we can instantiate that class with these 4 parameters, and we can call the fit function. So in fact, the fit function is still running. So we see that here the training has actually finished, so it is running now the evaluation part. Actually, I think there was previously a network issue, so that's why the the connection to the notebook was interrupted. So I will just have to reconnect. All right. So let's just go on from here. So after we have trained the model using this estimator.fit API, we can do some prediction. So let's just do some sentiment prediction here. So we can define this small function here, which just takes one sentence as an input, tokenizes it, looks up the indices associated with the tokens in the vocabulary. It prepends the class token and puts at the end the separator token, which is the standard format to input a sentence into the BERT model. Loads that onto our GPU with the MXND array. We set all the token types as 0 because we only have one token type here, and then we put that through the network, look at the output, judge if the first or second output element is greater, and return positive or negative depending on that. So if we do that based on this movie is so great sentence, you will get the positive output. So maybe we can also try if this BERT model can handle better negation. Okay, so again, I started running some other cells below, so we have to wait for them to finish before we can go back to this result here. So if we now take this fine-tuned model and we want to deploy that onto, let's say, some cloud service, so then we can export this model. So if it's a hybrid block, which we have called .hybridize on previously before we were training it, then it supports this .export function. So in this case, we just call net.export and specify a name, and then the model parameters as well as the model architecture will all be exported into a zip file, which contains these 3 files. Then we want to also export the vocabulary in our case. So we just write it to vocabulary.json, and then we decide to put these 3 into a tar.gz file, which is which is used by the SageMaker service as an input format. So after we have now saved these parameters and vocabulary and model architecture, I will show you how we can define or how we can interact with the SageMaker API, which is a service provided by AWS that allows you to run your models on AWS's resources. So essentially, you will just have to define the model and upload it, as I will show you next, and then you get kind of an endpoint, so which is some kind of URL, and you can use that within your application. So let's say you write some Android application or some website, and you want to make use of that machine learning model there. So whenever somebody opens your app, they may write some input text, and now you need to send that text to the endpoint. The endpoint will give you maybe the classification or whatever model you have trained and send back the response. And you won't have to care about provisioning enough GPUs or enough computational resources. So this AWS SageMaker service will automatically handle that provisioning for you and will always make sure that there's enough computational resources available to answer your users' requests, and that there's also not more resources used than necessary, meaning that you don't have to pay more than needed. Okay, so having saved these model architecture parameters and vocabulary, let's look how we can interact with the SageMaker. So for the SageMaker API, essentially what we need to have is we need to provide one entry point to that API. So in this case, we would create a file that is called serve.py, which is just a short Python file, which has to define two functions. One is the model function, which would be invoked by SageMaker once when the model is loaded, and then the transform function, which is invoked for every user request. So let's look at how we could implement this model function. So we have previously exported our model under the name prefix. We can import it now with this symbol block API. So the symbol block here, it can load any serialized architecture. So you don't need to have the architecture defined in Python as, for example, you don't need to have access to this class BERT model now, but you can just directly load the architecture from this JSON file. So we run this import, and we load the parameters from the params file that we saved before. We also open the vocabulary in this case, and we construct a tokenizer, and we return all three of them. And then in the transform function, we would get the model data, some input content type and output content type. So these would depend on the request type that the user does. So for us, the model here is actually equal to the three things returned in the model function. So the model here would be the network, the vocabulary, and the tokenizer. The request is just a JSON request. So we can load that with the JSON API in Python, and we get a sentence. And then we would call our predict sentiment function that we defined in the previous cell to get our result. And we just encode our result as a JSON string and return that in the response body, and also pass through the output content type here. So that predict sentiment function now is the same as we discussed before. So if we do that, then for SageMaker, we have to we can use some Docker container, which contains this serve.py file that we just created. So we can either use some pre-provided Docker container from the SageMaker team. So they actually do have some Docker containers for MXNet, also for other frameworks like a PyTorch or TensorFlow. So for the purpose of this tutorial, we will use a recent version of MXNet that is not yet provided natively by SageMaker. So we will just define our own Docker file here. So I define a Docker file as follows. So I just inherit from the Docker file used by the SageMaker team. So this URL you can find also in the documentation there. And I specify the region I'm running in. So we are currently using this US West 2 region. So for AWS, they have around the world, they have different data centers, and each of them is independent, so that if one of them maybe has an issue and gets down due to fire or whatever, then like other regions would still independently be working. So we specify the region that we're currently operating in. And we run some small command to install the right version of MXNet and of Glue and NLP. And then we build this Docker container. And then when we go on to the next step, we can import from the SageMaker API a model function. So that model function would then take our data file that we, in this case, have specified, have exported to this model.tar.gz file. We can input here the local URL to that file. We specify the image that we want this to run on. So this would be the Docker image that we have just created. So within AWS, there is a concept of roles. So for your account, you may, if it's your account, you will have administrative privileges. You can do everything with that account. But maybe you don't want your model to be able to do everything in your account. So you would assign it some certain role that has only very limited power. So it should actually only be able to execute the model and return the result. So it would get this kind of execution role, which is provided here also using the SageMaker API. We specify the Python version, and we specify the file that is used to, which contains this model function and transform function. So and once we have defined this SageMaker model, we can then deploy it. So for the purpose of this tutorial, we will just use the local deployment type, which means it will just run locally on your computer. But if you were to really deploy a model for some application, then you would actually specify here the compute instance type that you want to run on. So for AWS, they provide you with many different compute resource types. So for example, for this tutorial, we have the SageMaker notebook running on a P3 instance type, which is a compute instance that has NVIDIA V100 GPUs, which are quite fast. But depending on your use case, you may want to use another instance that has maybe only CPU and no GPU, or which has an older GPU, which would be cheaper. So you could specify that here. So let me just see what went wrong here. So I didn't save the file yet, apparently. So let us wait for exporting the model. So the BERT model is relatively large. It has many parameters. So compressing that takes a moment. Okay, that seems to be done now. So we have the Docker container already. So if you were to deploy your model now on the AWS SageMaker service, not in the local mode, but in the, let's say, standard mode where you choose some compute instance that it should run on, then the model data here shouldn't be a local file. So you would first have to upload your model to S3. So S3 is object storage. That is, yes? Which line? This line here? What error do you get?
For me, there was no space left, just that the Docker, when building the Docker here.
Okay, so maybe we use up all the space on the hard disk of this instance by running the previous notebooks, and now the Docker container fails to build. So what you can do to solve this problem is that you can go back here to this overview and just go to the root folder, and you can delete these two folders, the dataset folder and the model folder, and then that should free up some space. Okay, so the problem is here that we renamed something and didn't update it. So you would need to change this path here to have a 04 underscore deployment instead of the 06, and then the following call should work. So yeah, speaking of the location of this model.tar.gz file, now that we select instance type local, we can specify a local file here. But in a real world setting, you would export your model and then upload it to this S3 object storage, which essentially makes it available under some HTTP URL. You can, of course, configure if it's like readable by everybody on the world or just within your own AWS account. But it would be readable at least within your own AWS account, depending on, again, how you would set maybe this execution role here. And then when you would start or would deploy the model here and select the, let's say, p2.xlarge instance type, it would automatically set up as many instances as needed to run inference depending on how many user requests you get per second. So if you would get, let's say, 1,000 requests per second, then it would start multiple of these instances. For each of these, it would download the model file from the S3 URL provided and run the model function to load the weights and then run the transform function on each of the user requests, making sure that sufficiently many models are running to handle all requests. And then if there would be less requests at some point in time, it would start shutting down some of these instances. And then the way that AWS works is that you would be paying for whenever an instance runs, depending on how many seconds or like maybe milliseconds it runs. So when, yeah, they try to like run as little as possible. Okay, so after fixing the file name here, we find that the deployment works. So you get some output here from SageMaker, and then finally in the end it tells you that the model server started. So now there is a model server running, which is based on the model function and transform function that you have provided. And we can now use this predictor.predict API to query the model. So in this case, it will open a TCP connection to the port that your model is running on, and is providing it with this input sentence. The model is deployed, great, and then the model server will run the transform function on that input and will compute the sentiment label, and then will return the sentiment label. So that will then be sent back to you locally, and we get that as an output of this predictor.predict call, and then we just print it. So you could use this predictor.predict here in Python if you like, but actually the AWS SageMaker also provides the bindings in many other languages. So if you, I don't know, if you write maybe an Android app in Java or whatever language you like to use, you can use some AWS SageMaker SDK, and you would be able to get the predictor object there, given the name of the endpoint, and then that would automatically connect you to the model that you have deployed and would run inferences there when you send the requests. And but I mean, if you're done with that, then there's also the delete endpoint call, which you can use to free up the resources again. But maybe before that, if you have any other example sentences that you would like to query this model with, you can let me know, or you can try it locally. So are there any questions about how this works, or everything clear? Okay, so then as an exercise, I suggest you just try query this predictor with a few other sample sentences, and then if you're interested in deploying your model, you can find more information on this, like AWS SageMaker API on the API docs. And then finally, we will have another session which talks about a few tricks that we can do to reduce the amount of compute that we need to do during training or doing inference of our models. I will hand over to the next presenter then.
Okay, so this part will be a very quick overview of possible options in Google NLP that you can use to accelerate training and inference. So the key idea here is to reduce the precision of the computation with minimal impact on the performance. So once we reduce the precision, the main benefits is that obviously now you have lower memory bandwidth and memory consumption, and also it improves speed. And the main approaches that most frameworks use now is quantization, which means you can do inference in int 8 instead of float 32. And also mixed precision, which means you can do training and inference in FP16 instead of FP32. So to understand how this works, let's review how we represent these numbers in the computer. So for different data types, we have 2 to 3 parts in the bits that represents the data. So the first bit is the sign bit. And then for floating points, we have these exponential bits. And then for both int and the floating points, we also have the fractional bits. So you can see that different data types consume different number of bits, and then they can also represent numbers in different ranges. So FP32 has the largest range compared to other data types. And then if you use the simpler data types that whose representation has fewer bits, that means you will consume less memory, and the algebra computation will also be faster. Okay, so the idea of quantization is that we will do inference in integers. So, but the model is training FP32, right? So now we need to map numbers in FP32 to int 8. The challenge here is that they have different dynamic range, which means the minimum and maximum number can be represented using this data type. And they also have different resolution, which means within that dynamic range, how many unique numbers you can represent. So the approach is that if we know so let's say we have an operator, and if we know the min and max value of the output of this operator, we can scale that and map it back to the range of int 8. And a potential challenge here is that there can be outliers with very large or very small values. So then the scaling wouldn't be very efficient due to these outliers. So a common trick people use is to clip the min and max values to guard against the outliers. Okay, and then for accelerate BERT inference, this is a collaboration with teams at Intel. So we have a graph optimization, which means instead of having a sequence of operators, we can fuse that into a single operation. And in addition to that, we also have this post-training model quantization. So you can take any model training FP32 and then convert that into int8 so that you can run inference on CPUs. Okay, so here is some performance numbers for the BERT model. So here we say this is the core component of transformer, and the main computation is actually spent on matrix multiplication layer norm and this Gallo activation layer. So if we fuse these three operators, we can get some nice about 8 times speed up for these operations. And in addition to the operation, we can also do quantization on top of that using the Intel DLBoost library. So in this case, we reduce the model size from over 400 MB to 100 lower than 200 MB. And we also get around 2 times speed up on CPUs. Okay, so that's about int8 quantization for CPU inference. The next part will be about mixed precision. So here, compared to int8 with FP16, you can do both training and inference. But the challenge here is that because the dynamic range of FP16 is smaller than FP32, so then if you have very small gradients, which is which is a common problem in practical models. So then when you convert that to FP16, you would have a lot of zeroed gradients, and that impacts the model accuracy a lot. And also, so in this figure, you see that when we convert that to FP16, we also have lots of unused bits because all the numbers are concentrated in the middle. So this is naive conversion. The better things we can do is to scale the gradients before we convert them to FP16 so that we don't have this zero out problem and the wasted bits. And then after we do the FP16 operation, we would convert that back for FP32 operation. So that's why it's called mixed precision. So for some parts, we'll use FP16. The other parts will be using FP32. And as for which operators should be done in FP32, that will be an empirical question. So for example, for the sum operations, because there is potential overflow problem, we will mostly just do that in FP32. And then for implementation, so as I mentioned, we have empirical choices for the precisions of each operator, and also we have dynamic loss scaling. And here's the results on BERT inference. So we use the P3.2 large GPU on AWS, which is V100 GPU. And we run inference on the reading comprehension model trained on Scott. So we have about 2 times speed up with almost no accuracy drop. And for training, we have similar performance. So these numbers are for inference, but for training in general, we can also get 2 times speed up with no accuracy drop. So in summary, the main technique we can use to run to speed up model inference is reduced precision, because then when you use simpler data types, you have faster algebra operations and lower memory usage. And the 2 main approaches are using FP16, mixed precision, inference or training, and also int8 quantization for inference on CPUs. In both cases, we get about 2 times speed up with very little accuracy drop. Okay, so that is the end of the tutorial. So all of the materials are on the GitHub. so that you can go over the notebooks if you're interested later too. Anything else you want to add?
If you have any questions on any parts of the tutorial, feel free to come to us and we'd like to talk to you. All right, thank you very much.